Hey guys, so welcome back to your next class of catalyst concept. So in the previous class, we were looking at the functioning of a battery. We were looking at how does this battery exactly work, what's happening inside of this battery, right? So we came up with this thing wherein uh, we looked at the terminals of a battery, right? And the positive and the negative terminal, right? We saw the cathode, anode, or what you called it. We saw how all the positive charges were on one side and all the negative charges were on the other side. And due to this, there was a flow of electrons in the conductor that was connected to it, right? We knew that the electrons moved out away from the negative terminal and into the positive terminal. At the same time, inside the battery, all the negative particles, once an electron enters from here, a negative ion gets pushed to the other side and an electron will get pushed out from here, right? So there's this constant loop of negative charges moving inside of this circuit, right? Whenever it is connected, electrons inside a battery, and again the charge is moving inside of the battery and another electron just coming out of the other end into the conductor again, right? So when it comes to a battery, we can also define what is happening inside the battery in certain quantitative terms, right? As is in physics, we need to measure things to find out like how big or small they are, right? So uh, we can also, if you remember a while ago, we had one class where we spoke about the work done, right? We said we talked about something called, I think, potential difference, right? We saw a W by Q equals to Fe in L divided by Q, right? So this was something that we defined as what is the potential uh, difference, right, across a conductor, across the two ends. Today we're going to look at something that's very similar but within the battery, right? So when this movement is happening, we spoke of two forces, right? We spoke of something called a chemical force, what we call as Fc, and we spoke of an electric force called an Fe, right? Typically what happens when this process happening, both these forces are equating, right? That is why the loop goes continuously, wherein as the electrons are moving out in the battery, they're also getting out of the battery. So they, what we call, they come to a state of what we say equilibrium, wherein both the forces are parallel to each or equate to each other. Okay. So what I want to find out today is what is the work happening inside a battery? How do I measure it? So if I take a battery that looks like this, right, the positive and the negative, let me look at the distance over here. Okay, let me call this distance as D, nothing but the length of the battery between the terminals. Okay, so now since we're talking about negative charges moving, let's just take the in the context of negative charge. We know negative charges can move from one end all the way to the other end, to the negative end, right? From positive to negative terminal. Now, if I have to calculate the work done there, I will say work done is nothing but force into displacement, right? As we had learned previously. So now I know that this force is nothing but chemical force, right? We already spoke of chemical force inside the battery, which actually splits the positive and negative ions separate. So I can say that this work is nothing but Fc into displacement. Okay. Now, how much is this displacement that I'm talking about? In the conductor, we said we'll take a length L of conductor and we calculated it for that. But over here, our battery's length is set, right? It is the distance between the two terminals. Let's call it like how we called it D over here. So I can say work done is nothing but Fc into d, chemical force into the distance. Now, if I want to find out work done on unit charge, okay, say this is work done on Q charge, okay, because we don't know exactly how much charge is it, let's just call it Q. Okay, if I want to find out what is the work done on a unit charge, on a single charge, or let's be more specific, on a single negative ion, then what I will do is I will divide this work with the total charge. Okay, so work done per unit charge or on unit charge, either way, which comes out as nothing but Fc into D divided by Q, right? Now, we also know one thing, that is Fc and Fe are equal, right, from this relation over here. So this W by Q, I can also write it as Fe into D divided by Q. Okay. Now, the reason why I switched from Fc to Fe is because Fe is a value that we already know. Okay, electric force is something that we've already measured previously and is also something that can be measurable in general. Okay, so I'm simply just substituting it with a value that we know. Okay, so this is nothing but the work done per charge or per unit charge inside of a battery. Okay, keep in mind, when you talk about voltage, you're talking about across the conductor from one end to the other end. When you're talking about EMF or this one, it is inside of the battery. This work is nothing but inside the battery. So I will call this as electromotive force. Okay, electromotive force. It's a big word, but its meaning is very small. Electro is the charge, motive is to move, and force. Force that moves the charge. Very simple way to remember it. Okay. So electromotive force is nothing but this W by Q, which is nothing but Fe into length or the size of the battery, the distance between the terminals, divided by the total charge being moved across the battery. Okay. Now, there is a symbol for this electromotive force. It is called as epsilon. Okay, it's called as epsilon. It kind of looks like a very curvy E, kind of like how we have cursive E. We write cursive E like this. Similarly, we just write it kind of like this. This is what an epsilon symbol looks like. It's again a Greek alphabet. So you can just kind of write it like that. Okay, that is epsilon. Actually, the bottom part you don't need to curve. Just write it like that. Okay. All right. So electromotive force is also called as EMF in short. Okay. So EMF epsilon is nothing but FE D divided by Q. I can also define it like this. All right. So if I have to define electromotive force, I'll say it's the amount of work done on a unit charge to move it from the unit positive charge, to move it from negative terminal to positive terminal. Okay, although we calculated for moving negative charge from positive to negative terminal, when we define it, we can also call it for positive to negative. Okay, because this is the direction of the electric field. However, it doesn't really matter. It'll come up to the same value. Okay, positive to negative or negative to positive, the value is the same. Okay, just in terms of definition, this is something that you can remember. Work done, unit positive charge to move from negative terminal to the positive terminal through the battery. Okay, not out from outside, through the battery. All right. Now this is all for today. So this EMF is actually very similar to the voltage that we spoke about, like I already mentioned. The what we had measured previously, EMF and voltage, they are also measured in pretty much the same way. So EMF also has the pretty much the same units, which is nothing but volts. Okay. Now, how do we measure this is one thing, right? I told you Fe is a value that we already know. And how do we already know that? Is because we have a machine to measure it. Okay, it's nothing but what we call as a voltmeter. Okay, now voltmeter is something that you might have seen. It's like this yellow colored box that electricians and all use. It has like two probes. You can just put them in two places and it shows you a reading, right? So it's also called multimeter, right? So that's a device that is used to measure current. In the next class, I'll even probably try to show you that machine, how it looks. As of now, just try to think about it, right? That's it for today. This is where I'm going to end today's class. The next class, we'll look at the next topic. All right. If you have any questions, doubts, please drop them in the comments below. And thank you so much. Bye-bye.